Just to illustrate that there is a conflict between mathematics and physics. So I would now end, as I put it, how much harm has wrong kind of mathematics done to physics over centuries? I think this is now that part of the story of the marriage of mathematics and physics where things go wrong. This is how my metaphor which I use. As in every marriage, there is such a phase, I guess. So you see, you have the problem already starting from Newton and Maxwell. This is, of course, the problem with the application of continuum mathematics, or the mathematics of linear continuum. The problem actually dates all the way to Zeno's paradoxes, if you wish. But let's stick to Newton, because that's when proper physics begins, or we could say. If we disregard Archimedes, who obviously knew a lot about ideas of mechanics, and he had started developing calculus, but the problem is that most of his works are lost, so we cannot really judge. So if we begin with Newton, you have it, the same problem as with Maxwell, but let me illustrate it on the example of Maxwell's electrodynamics, because I mean, it's the same type of formula, it's the same structure for gravitational force, but I will illustrate it deliberately for electric force, because this problem is later transferred to quantum electrodynamics, which I said was the problem Feynman was working on. So, and he gloriously said, or famously said, that he gloriously failed, right, by solving it. So the problem is the following. You have simple question. If the force, electric force between charges, is dropping as an inverse square, so it's becoming less and less with the square of distance, then if you want to calculate the energy or work done by bringing one charge in the vicinity of the other, say from A to B, you are supposed to do an integral, a sum, let's put it that way. So this integral, however, will keep the form of the equation. Basically, you will just get 1 over r. So it will still be a hyperbolic dependence, which creates problem, because as you know, we cannot divide by 0. Namely, the question is this: what happens if those two charges come very close? So if you are actually going more and more inward towards the center of the field or the force. So obviously the distance is decreasing. So you are more and more, you're getting a smaller and smaller value of R and bigger value of W, or energy, which means ultimately you would get a divergence. So you would, what we popularly say, you would divide by 0, but technical term is divergence. So you would have a diverging integral, which means that the energy of the field would be infinity, which is of course absurd, and you don't have to be a physicist or mathematician to judge that, because the whole of science is based on the fact that everything is finite. The universe and all the quantities, and therefore the energy. And by the way, if the energy would be infinite, you would have something like perpetuum mobile of the first type, I guess. So, you know, you would have all these ancient problems cropping up again. So this problem, if you think that this is an isolated case and this is just a matter of a wrong approximation, this could be improved. No, because this problem continues to quantum electrodynamics. I will just skip this for the moment because I actually should have put this slide before. So in quantum field theories, and by the way, all the way to superstrings, this modern day generalizations, you have this problem which is called renormalization, which means, this is in Feynman, the famous Feynman diagram representation. So imagine, which is particularly simple to understand, that's why we are using it. So even if you're not a physicist, again, should be quite straight, let's say, if not straightforward, pictorial. So imagine 2 electrons, which are 2 charges. You see, the illustration is actually animation, so you can see where we start. Time is on the vertical. So the electrons are coming from below, and they are simply colliding. In physics, we of course know there are no collisions as a direct contact collisions, like Descartes thought. They actually come at certain separation, and then minimal separation, then they move apart. So you see that this tree diagram branches off again. In between, they exchange a photon, the so-called virtual photon, which is the sign of energy exchange, which is basically a quantum field theory way to explain the energy of the field. Okay, so The interesting part is of this diagram, I mean, there are different features, but the interesting part for the moment is you see these points where vertices meet. So basically, there is a point of, let's say, interruption. So the line is not smooth, right? So if the line is not smooth, there would be a problem. So you cannot calculate integral as your integral will not be converging. So this is a translation of what's being done by purely algebraic means or analytical means. So, and people knew that, and this is a big problem for Feynman was of course aware of this. But how they resolve this? So, for instance, in quantum electrodynamics, you don't just calculate energy; you calculate more than energy. You calculate the constants. Remember, I said that we started with that. Physicists, in Wigner's account, physicists want to know why some constants appear, so like pi or E or the mass of electron or whatever. So quantum field theory is a big progress in physics meant a big progress in physics because for the first time physicists were able to calculate constants, which was Einstein's big dream that we should find an equation with only one constant. Or actually, he said this is the ideal of string theory, which is far from Einstein's ideal. Einstein's ideal that there are no inexplicable constants. The constants are just pure numbers, like 1/2 and p and pi and I or E. The point is, physics is nowhere near that. But the point is that physicists are able to calculate some of the constants. But how do they do it? They introduce this quite unnatural process, which is called renormalization, which actually means eliminating, there is a way, believe it or not, there is a way of eliminating infinities. And people won Nobel Prizes for that as well. I corresponded with one of them, this Professor Hoft. But it's, as Feynman said, in the 60s, so this was development in the 70s and 80s, but as Feynman already said, in 60s, this is an artificial procedure, which even mathematically speaking is quite problematic, and they made an effort to make it mathematically consistent. Don't ask me how, because I actually don't believe them. They've managed, and from what I know, it doesn't make sense to me. I'm talking now in terms of interpretation, not in terms of just consistency, mathematical consistency. So the problem is that you still have these issues arising from the application of set theory and a linear continuum. Of course, you know, I believe everybody knows that modern mathematics is built on the ideas of set theory. And there is no set theory, properly speaking, without the idea of linear continuum and the upgrades to that, so the higher level cardinalities. So the problem is how will you live with such mathematics, which actually so gloriously fails when we need to figure out the mass, something like the mass of electron, we get the infinity, and then we need to remove the infinity. You know, the common practice in physics is that you remove the very small contribution, the correction, so to speak. You do not remove the very big or very large correction, so part of the calculation. In this case, you are removing all of it because you're removing the infinity. You know, because infinity plus something very small is still infinity. So this is the problem. By the way, you have similar problems in quantum mechanics with application of uncritical acceptance and let's say import of mathematical structure, excess mathematical structure. You have the complex numbers, so which were debated from their inception in the 70s or 18th century. But the problem is how seriously we should accept them in mathematics. But in physics, you see, they already appear in electrodynamics, but they are there just an expediency and calculation. So it's just a calculation device. You don't actually need to rely on complex numbers, you know, the imaginary I, or again, higher order complex numbers, which are called quaternions or octonions nowadays. They even apply in physics. The problem is you don't really need to, in quantum, in classical electrodynamics, to refer to these complex numbers in interpretation, at the level of interpretation. There is no need. So Maxwell's theory is safe in that respect. But already special relativity, I would argue, is not safe. But somehow this passed unnoticed, let's say, unnoticed. Because after Minkowski introduced it, it was not Einstein who introduced this complex Minkowski space into physics, but it was his mathematics professor Minkowski. Somehow or another, this gained more and more popularity. I still am not sure how it actually happened, but I read a lot, and I'm still not sure why it was passed unnoticed that the famous four-dimensional space-time continuum is not actually four-dimensional. I mean, Einstein famously declared that time somehow becomes like space, but it's not, because time coordinate is not t, like the x, y, and z. It's actually I, c, t, so it contains imaginary unit, so it cannot be considered as equal. By the way, the original Einstein paper did not have that, so he had much, let's say, much more reasonable view. He doesn't talk about four-dimensional continuum, but of course Einstein needed that excess structure to develop the special relativity in what later became general relativity. So he couldn't do without the complex numbers. And in quantum mechanics, but somehow, again, you avoid them at the level of interpretation, somehow. I'm not saying actually that this could be justified as complete avoidance, but let's say somehow. Because the problems, again, arise in cosmological questions about the edge of the universe, about the beginning of the universe, the end of the universe. You have there complex numbers rising again to mess the plans of rationalistic physics. So,
in order to leave some room for discussion, how you go to the end?
Yes, let us move, because I think this, yes, you're right. This is enough for illustration, and we are then basically at the end. So I would now say here, modes of reasoning in mathematics and physics. This is my proposal, one of the solutions at the logical level, and Professor Chobak and I published recently a paper. Can physics, after all, be a deductive science? So I will just say that she did research on this before, just at the level of analogy, and we together tried to wed, let's say, these logical considerations she already had, and my approach from borrowing from Wigner. This is one of his other papers, where he says, so this, I think Wigner already has an answer to his problem, why mathematics is successful, but he did not connect, interestingly enough. So what I take from Wigner here is, he has, you see, a structure of all physics, split into several levels, let's say. So the first level is observation, the initial condition plus initial conditions. Then you have correlations of observations, which Wigner calls laws. Laws in the sense of first approximations, models, which we said were plagued by all sorts of deficiencies. But then you have the correlations of correlations, which must be quite abstract and most general in order to be universal. And these are actually, I told you, he developed later this symmetry approach to physics, where the symmetry so-called symmetry principles, for our purposes here, we can say just conservation laws, they're connected, like the law of conservation of energy or charge. These are the most general principles. And Wigner says that in order to justify any statement in physics, we need to appeal to those most general laws, which has a flavor, willing or not willing, when you think about it, it has a flavor of deductivism, right? You are deducing something from first principles. You are not, which must be assumed even to be able to do the experiment. By the way, this is how the experiments are done in particle physics. You first check whether a certain reaction, which you would do in CERN, of collisions of particles, usually, whether it actually fulfills these laws of conservation. And therefore, I'm saying this is a sketch, and so in discussion, let's discuss more. You would have that physics is somehow to do with mathematics. Physics is somehow mathematical. Whether physics is part of mathematics or whether mathematics is part of physics, this is another topic. But I would say Wigner already offers in other papers, mainly on symmetry, offers a solution to his problem, at least part of his problem, which is that physics must be somehow made a deductive science. Of course, this, when I say deductive, I don't mean that physics will ever cease being empirical. So I will end with this. By empirical, but we just need to define terms. Empirical means physics needs experiments because no physicist will ever be all smart and have all the principles. It's unlikely. And therefore, especially for the more applied branches of physics, you will need to ask nature, let's put it that way. But for the most general rules of the game in physics, presumably we should, with further effort, get to certain number of them, if not all, and be able to make deductions. And moreover, the specific statements of sub-branches of physics, different branches of physics, especially applied or more applied, will depend on these. So I will end here. This is more or less what I meant to say anyway, so open for discussion.
Thank you very much. Can you move this presentation?